Welcome to Gamma Classroom. Today I'm going to introduce 1.2 Ohm's Law, Part 2. 1.2-4 Calculating electrical power. We have seen the formula for determining the power in an electrical circuit by multiplying the voltage in watts by the current in amperes. We arrive at an answer in watts. Let's apply this to a circuit example. P equal to I times E. In the circuit, we know we have battery voltage of 18 watt. This 18 watt. And a lamp resistance of 3 ohms here. Using Ohm's law, this Ohm's law, to determine current. So this is I equal to E divided by R. We know the E, the battery voltage, is 18 watt. And the resistance of the electric lamp is 3 ohm. And so 18 divided by 3, we get 6 amp for the current. This is 6 amp. We know the formula for the power, the electrical power, P equal to I times E. This means current, 6 amp. And the voltage, the battery voltage, is 18 watt. So we can get 108 watt for the power. Let's try taking that same circuit and increase the battery voltage to see what happens. Intuition should tell us that the circuit current will increase as the voltage increases, and the lamp resistance stays the same. Likewise, the power will increase as well. Now, the battery voltage is 36 watt instead of 18 watt. The lamp is still provide 3 ohm of electrical resistance to the flow of electrons. The current now is, according to the Ohm laws, the current equal to E divided by R. This means equal to 36 watt. This is 36 watt. And divided by 3 ohms. This is 3 ohms. So the current equal to 12 amp. And the power, now we have the 12 amp current instead of 6 amp in the previous circuit. For now, the power equal to I times E. The current is 12 amp. And the voltage of the battery is 36 watt. 12 times 36, we can get 432 watt. Since we know the power P equal to I times E, if we only know voltage and resistance, how to get the power directly do the calculate with voltage and resistance. We can use algebra again to manipulate the formula. We can take out original power formula and modify it for applications where we don't know both voltage and current. We know the current equal to E divided by R, and the power equal to I times E. So we can use the current, this formula, replace the I in the power formula. So you can equal to E divided by R, then times the E. Then we get two E's here. So the power formula can change to P equal to E squared divided by R. It means the power, if we only know the voltage and the resistance, so we can directly do the calculation, use E squared divided by resistor. We can get the power. Similar, if we only know current and resistance, how to get the formula? Directly from current and resistors. We know E equal to current times the resistance, means equal to I times R. And P, the power, is equal to I times E. Since the P equal to I times E equal to I times R. You see, this is I, this I. And the E is equal to E equal to I times R. You replace the E, use I and then R here. So we get the formula equal to I squared times R. Because they have the two I, use I times I equal to I squared. And this is R. So P equal to I squared times R. A historical note. It was James Prescott Joule, not George Simon Ohm, who first discovered the mathematical relationship between power dissipation and current through a resistor. This discovery, published in 1841, followed the form of the last equation, P equal to I squared times R, and is properly known as Joule's law. However, these power equations are so commonly associated with the Ohm's law equations relating voltage, current, and resistance is E equal to I times R, and I equal to E divided by R, and R equal to E divided by I, that they are frequently credited to ohms. Joule's law power equations, we know P equal to I times E. Also, P equal to E squared divided by R, or P equal to I squared times R. All three are Joule's law. We should remember those formulas as an electrical engineer. 1.2-5 Resistors. Because the relationship between voltage, current, and resistance in any circuit is so regular, we can reliably control any variable in a circuit simply by controlling the other two. Perhaps the easiest variable in any circuit to control is its resistance. This can be done by changing the material, size, and shape of its conductive components. Special components, called resistors, are made for the express purpose of creating a precise quantity of resistance for insertion into a circuit. They are typically constructed of metal wire or carbon and engineered to maintain a stable resistance value over a wide range of environmental conditions. Unlike lamps, they do not produce light, but they do produce heat as electrical power is dissipated by them in a working circuit. Typically, so, the purpose of a resistor is not to produce usable heat, but simply to provide a precise quantity of electrical resistance. We have already learned the resistance in previous video. The most common schematic symbol for a resistor is a zigzag line, like this. In a schematic drawing, you will always see the resistor like this. If you see this zigzag line, it means it's a resistor. Resistor values in ohms are usually shown as an adjacent number. And if several resistors are present in a circuit, they will be labeled with a unique identifier number, such as R1, this R1, R2, R3, exact. As you can see, resistor symbol can be shown either horizontally or vertically. So this is R1. So this is 150 ohm. This means this resistor's value is 150 ohm, and the number is R1. And this one is R2. It's because in the same circuit we will only unique identifier number. So R1, R2, R3 exactly. So the number is the value of the resistor is 25 ohm. Real resistors look nothing like the zigzag symbol. Instead, they look like small tubes or cylinders with two wires protruding for connection to a circuit. Here is a sample of different kind of and size of resistors. You see, this one is like the tuber is resistors. The value of the resistor is 200 ohm, and it shows 12 watt. 12 watt means if the current in some value and the resistors dissipate the power 12 watt or less, this resistor is safe to use. If the current is greater than is increased and the power dissipated on this resistor is greater than 12 watt, this resistor will be overheat. We can calculate the current, what current is safely passed through the resistor. We know the Joule law, P equal to I squared times R, and I squared equal to P divided by R. The P we know is 12 watt, so it's 12 watt, and the resistor is 200 ohm. So 12 divided by 200 is equal to 0.06. This is I squared equal to 0.06. And then the I equal to 0.245 N. It means when the current passes through the resistor, the current is equal to 0.245 N or less. This resistor is safe for use. The heat not overheat. If the current is greater than 0.245, this resistor will get overheat. And this one, you see, this is like the cylinder. They have two legs, this one and this one. Here I have two legs, so this one and this one. Because the resistor there is no direction. You can connect this leg to the power positive, or you can connect this point to the power negative, and this leg connect to the power positive. It does matter the same. The current passed through the resistor is the same value. Only difference is the current direction. If this connects the power positive, the current will go this way, flow to this side. Reverse the same. If this leg connect to the power positive, the current will go this way, pass through the resistor, go through this leg, go back to the power negative pole. Negative. Same thing. This resistor, you see there are radiators on the top on the outside of the resistor. This means this can dissipate the heat when the current passes through the resistors and generate the heat, and the heat will go through the radiate and dissipate to the air. Same thing, this resistor without direction. You can connect this point to the positive, or you can connect this pole to the positive. And this is 30 watt. And this is 40k ohm, means 40,000 ohm. So you can do the calculation similar with this, use this formula. And the power is 30 watt, and the resistor is 40,000 ohm. you can get the current, and this is the same. We already learned this resistors, how to identify the value. If you are interested, please go back to see our previous video. So this means 10,000 ohm and with half watt. So they have two legs. One, the another leg in this side. They have the color code. Here you can find the exact value according to the color code. Similar, this is 150 kilo ohm with 1 and quart. It's called watt. This is 1.5 kilo ohm with 1/8 watt. In keeping more with their physical appearance, an alternative schematic symbol for a resistor looks like a small rectangle box. So you will see the resistor in schematics either way. One showing use the rectangle box with two legs, or use the zigzag with two legs. They are the same, both showing the resistors. Similar, you can use the vertical, is the same, horizontal or vertical. Resistors can also be shown to have varying rather than fixed resistance. This might be for the purpose of describing an actual physical device designed for the purpose of providing an adjustable resistance, or it could be to show some component that just happens to have an unstable resistance. When you see the resistors with zigzag or rectangle, but in the simple, they have an arrow like this. The arrow showing like this. The arrow, this is the arrow here showing. This means this resistance value can be changed, or called variable resistance. You can change the value of the resistor or change the value of this resistor. In fact, anytime you see a component symbol drawn with a diagonal arrow through it, that component has a variable rather than a fixed value. The simple modifier means the diagonal arrow is standard electronics simple convention. Variable resistors must have some physical means of adjustment, either a rotating shaft or lever that can be moved to vary the amount of electrical resistance. Here is a photograph showing some devices called potentiometers, which can be used as variable resistors. You will see this and this one. This all is available. This means they have three legs, right? You can change any value between the three one. You can connect this point with this point with different value of the resistor. Or you can connect this leg and in the bottom legs, the resistance value will be changed. Or you can connect this leg with this. So these two legs, the resistance will be changed. Similar is with this one. You can connect this leg and this leg. The resistor is 1. If you connect this leg with this leg, the resistor value is different with this two leg. Or you can connect this leg with this one. This value of the resistor is different with this one or this one. Sometimes this two leg means this value plus this value. And this, you see this adjustable resistor, you can use a screwdriver, turn this, you see this have the slot here, or the slot here. Use the screwdriver and turn or clockwise or anti-clockwise, different way, the value of the resistor can be changed. Also, you have 3 legs here. You can connect to these 2 legs or connect these 2 legs. The resistor value different. Or you can connect these 2 legs. Similar is the same. You can connect these 2, or you can connect these 2. Or you can connect this one and this one. It's different value of the resistor. Because resistors dissipate heat energy as the electric currents through them overcome the friction of their resistance. Resistors are also rated in terms of how much heat energy they can dissipate without overheating and sustaining damage. Naturally, this power rating is specified in the physical unit of watts. Most resistors found in small electronic devices, such as portable radios, are rated at a quart 0.25 watt or less. The power rating of any resistor is roughly proportional to its physical size. We already introduced this resistor with 10 kilo ohm and half watt. Half watt is 150 kilo ohm and a quart watt. Yeah. Note in the first resistor photograph how the power ratings relate with size. The bigger the resistor, the higher its power dissipation rating. Also note how resistance in ohms have nothing to do with size. Although it may seem pointless now to have a device doing nothing but resisting electrical circuit, resistors are extremely useful devices in circuits. Because they are simple and so commonly used throughout the world of electricity and electronics, we will spend a considerable amount of time analyzing circuits composed of nothing but resistors and batteries. For a practical illustration of resistors' usefulness, examine the photograph. It is a picture of a printed circuit board, or called PCB. An assembly made of sandwiched layers of insulating phenolic fiber board and conductive copper strips, into which components may be inserted and secured by a low-temperature winding process, called soldering. The various components on this circuit board are identified by printed labels. Resistors are denoted by any label beginning with the letter R. Let's see the amplified picture in next. If you see any labels beginning with R, like this R1, it means this is the resistors. Resistors number 1. And this is R2, means resistors number 2. You can see here R7. This means resistors R7. This is R9. This is a resistors. This is number 9. The another one is an R10. It means it's the resistor connect to this way. It's number 10. Resistor number 10. And so on. If you see any labels start beginning with R, it means resistors. You can find the resistors value according to the color code. You have different color. It means different resistance values. We can find all the other resistance in this PCB. You see here is R5, the resistor R5. So R6, this is the resistor. Then another R4, R12, this is resistor. Here, what's the number? R1. And they have the different colors, are different resistance. So when you see any label beginning with R, that means it's resistors. And you can find all the resistor value according to the color code. If you understand what color code, so you can find the value. Another circuit board example shows resistors packaged in even smaller units, called surface mounting devices. This particular circuit board is the underside of a personal computer hard disk driver. And once again, the resistors soldered onto it are designated with labels beginning with the letter R. We can see here is the resistor R1, R4, and R5. Here's R2 and R3. You can find a lot of the resistor in this board. There are over 100 surface mount resistors on this circuit board, and this count of course doesn't not include the number of resistors internal to the black chips. These two photographs should convince anyone that resistors devices that merely opposes the flow of electrons are very important components in the realm of electronics. In schematic diagrams, resistor symbols are sometimes used to illustrate any general type of device in a circuit doing something useful with electrical energy. Any non-specific electrical device is generally called a load. So if you see a schematic diagram showing a resistor symbol labeled loud, especially in a tutorial circuit diagram explaining some concept and related to the actual use of electrical power, that symbol may just be a kind of shorthand representation of something else more practical than a resistor. To summarize what we have learned in this lesson, let's analyze the following circuit, determining all that we can from the information given. The battery voltage is 10 watt, and the current is 2A in the circuit. What is the resistance and the power displayed on these resistors? All we have been given here to start with is the battery voltage, 10 volts, and the circuit current, 2 amperes. We don't know the resistor's resistance in ohms or the power dissipated by it in watts. Surveying our array of almost null quantity equations, we found two equations that give us answers from knowing quantities of voltage and current. R equal to E divided by I. It means the resistor equal to voltage divided by current, and the power is equal to current times the voltage. Inserting the knowing quantities of voltage E and current I into these two equations, we can determine circuit resistors R and the power dissipation P. R equal to voltage divided by current. The voltage is 10 volts and the current is 2 amp, so equal to 5 ohms. And the power dissipated on the resistor equals the current divided by the voltage is 2 amp and 10 watt equal to 20 watt. Let's continue on 1.2-5, non-linear conduction. Ohm's law is a simple and powerful mathematical tool for helping us analyze electrical circuits, but it has limitations, and we must understand these limitations in order to properly apply it to real circuits. For most conductors, resistance is a rather stable property, largely unaffected by voltage or current. For this reason, we can regard the resistance of many circuit components as a constant, with voltage and current being directly related to each other. For instance, our previous circuit example with the 3-ohm lamp, we calculate the current through the circuit by dividing voltage by resistors. Is I equal to E divided by R. E is 18, R is 3, so the current is 6 amp. Doubling the battery voltage to 36 volts result in a doubled current of 12 amperes. All of this makes sense, of course, so long as the lamp continues to provide exactly the same amount of friction, or called the resistance, to the flow of electrons through it is 3 ohm. We can compare the two circuits. In this circuit, the battery voltage is 18 volt. The current is 6 amp. If we double the battery voltage to 36 from 18 volt, and the current will be changed from 6 amp to the 12 amp. The voltage is double this one, 18 to 36. So the current will be double too, from 6 amp to 12 amp, because the lamp resistance is keep 3 ohm. This is the 3 ohm too. However, reality is not always this simple. One of the phenomena exploited in a later video is that of conductor resistance changing with temperature. In an incandescent lamp, the candle employing the principle of electric current hitting a thin filament of wire to the point that it glows white hot. The resistance of the filament wire will increase dramatically as it warms from room temperature to operating temperature. If we were to increase the supply voltage in a real lamp circuit, the resulting increase in current would cause the filament to increase temperature, which would in turn increase its resistance, thus preventing further increases in current without further increases in battery voltage. Consequently, voltage and current do not follow the simple equation I equal E divided by R, with R assumed to be equal to 3 ohm. Because an incandescent lamp's filament resistance does not remain stable for different currents. The phenomenon of resistance changing with variations in temperature is one shared by almost all metals, of which most wires are made. For most applications, these changes in resistance are small enough to be ignored. In the application of metal lamp phenomena, the change happens to be quite large. This is just one example of non-linearity in electrical circuits. It is by no means the only example. A linear function in mathematics is one that tracks a straight line when plotted on a graph. The simplified version of the lamp circuit with a constant filament resistance of 3 ohm generators a plot like this. If we put the horizontal axis as the voltage E and the vertical axis as current I, if we're given a voltage called E1, then we can calculate the current I1. The similar, if we given voltage E2, then we can get the current I2. And E3, we can get the current I3. Even more, you can do the same. If we draw the line horizontal from the I1 and a vertical line from E1, the crossover point is here. Here we call 1.1. Similar, we can call it 0.2 and 0.3. We can see all the points were located on a straight line. Means if you connect all the points, we can form a straight line from this point, even go to forever. And this angle is constant. We call this circuit as a linearity circuit because the resistance in this circuit is constant. The straight line plot of current over voltage indicates that resistance is a stable, unchanging value for a wide range of circuit voltage and currents. In an ideal situation, this is the case. Resistors which are manufactured to provide a definite stable value of resistance behave very much like the plot of values seen above. A mathematician would call their behavior linear. A more realistic analysis of a lamp circuit, however, over several different values of battery voltage would generate a plot of this shape. If we put the horizontal axis as a voltage E and the vertical axis as a current I, when given one point of the voltage, then we can calculate the current in this point. They can find the point, crossover point is here. And if we give different voltage here, then we can get the different current. As so on, we can give different voltage point. Then we can get different current in this point. If we connect all the points together, you can see this point together is not on a straight line. It's on a curve line like this. That means the voltage, the resistor value in this circuit is not constant, it's variable. We call this circuit as a non-linearity circuit. It means the resistor in this circuit is not constant. If we try to apply Ohm's law to find the resistance of this lamp circuit with the voltage and the current values plotted above, we arrive at several different values. we could say that the resistance here is non-linear, increasing with increasing current and voltage. The non-linearity is caused by the effects of high temperature on the metal wire of the lamp filament. Another example of non-linear current conduction is through gases such as air. At standard temperatures and pressures, air is an effective insulator. However, if the voltage between two conductors separated by an air gap is increased greatly enough, the air molecules between the gap will become aerolyzed, having their electrons stripped off by the force of the high voltage between the wires. Once aerolyzed, air and other gases become good conductors of electricity, allowing electron flow where no could exist prior to aerolyzation. If we were to plot current over voltage on a graph, as we did with the lamp circuit, the effect of aerolyzation would be clearly seen as non-linear, as like this. The same, we put the horizontal axis as voltage and the vertical axis is the current I. When the voltage is in this area before 200, there is no any current flow through this circuit. When the voltage is increased to this point, we can see a little bit what current will pass through the circuit. As the voltage increase to this point, the current is increased accordingly. At this point, when the voltage reaches this point, we call the aerolyzation potential. When the voltage reaches this point, the current will increase dramatically, very fast from this point, increase to this point. So when the voltage keep going to increase, and the current will increase like this point. Even the voltage reach this point, the current almost keep the same, but this very big. So we call this is the non-linear circuit. Incidentally, this is the reason lightning bolts exist as momentary surges rather than continuous flows of electrons. The voltage built up between the Earth and the clouds, or between different sides of clouds, must increase to the point where it overcomes the aerolyzation potential of the air gap before the air aerolyzes enough to support a substantial flow of electrons. Once it does, the current will continue to conduct through the aerolyzed air until the static charge between the 2 points depletes. Once the charge depletes enough so that the voltage falls below another threshold point, the aerolyzed and returns to its normal state of extremely high resistance. Many solid insulating materials exhibit similar resistance properties. Extremely high resistance to electron flow below some critical threshold voltage, then a much lower resistance at voltages beyond that threshold. Once a solid isolating material has been compromised by high voltage breakdown, as it is called, it often does not return to its former isolating state. Unlike most gases, it may isolating once again at lower voltages, but its breakdown threshold voltage will have been decreased to some lower level, which may allow breakdown to occur more easily in the future. This is a common mode of failure in high voltage wiring. Isolation damaged due to breakdown. Such failures may be detected through the use of special resistance meters employing high voltage, 1000 watts or more. They are circuit components specifically engineered to provide non-linear resistance curves. One of them being the varistor. Commonly manufactured from compounds such as zinc oxide or silicon carbide. Those devices maintain high resistors across their terminals until a certain firing or breakdown voltage equivalent to the analyzation potential of an air gap is reached, at which point their resistance decreases dramatically. Unlike the breakdown of an insulator, varist breakdown is repeatable. That is, it is designed to withstand repeated breakdowns without failure. This picture is showing a varist. This is a varist. Other electrical components exhibit even strange current voltage curves than this. Some devices actually experience a decrease in current as the applied voltage increases. Because the slope of the current voltage for this phenomenon is negative, angling down instead of up as it progresses from left to right. It is low as negative resistance. Let's take a look at this picture. In this graph, we can see this curve in this area is positive when the voltage increase and the current will increase too. But in this area, from this point to this point, when the voltage increase, but the current will decreases. So we call this area negative resistance. Most notably, high vacuum electron tubes, known as tentrons, and semiconductor diodes, known as Esaki or Tudor diodes, exhibit negative resistance for certain ranges of applied voltage. Ohm's law is not very useful for analysis the behavior of components like this, where resistance varies with voltage and current. Some have even suggested that Ohm's law should be demoted from the status of a law because it is not universal. It may be more accurate to call the equation R equal to E divided by I a definition of resistance, befitting of a certain class of materials and a narrow range of conditions. For the benefit of the student, however, we will assume that resistance specified in example cycles are stable over a wide range of conditions, unless otherwise specified. We just want to expose both you to a little bit of the complexity of the real world, lest we give you the false impression that the whole of electrical phenomena could be summarized in a few simple equations. This is the all that we should learn today. Let's review the main points that we already learned in this video. Number 1. Devices called resistors are built to provide precise amounts of resistance in electrical circuits. Resistors are rated both in terms of their resistance, ohms, and their ability to dissipate heat energy, watt. Number 2. Resistance ratings cannot be determined from the physical size of the resistors in question. Although approximate power rating can, the larger the resistor is, the more power it can safely dissipate without suffering damage. Number 3. Any devices that performs some useful task with electrical power is generally known as a load. Sometimes resistor symbols are used in schematics diagrams to designate a non-specific load rather than an actual resistor. Number 4. The resistance of most conductive materials is stable over a wide range of conditions, but this is not true of all materials. Number 5. Any function that can be plotted on a graph as a straight line is called a linear function. For circuits with stable resistance, the plot of current over voltage is linear, I equal to E divided by R. Number 6. In circuits where resistance varies with changes in either voltage or current, the plot of current over voltage will be non-linear, not a straight line. Number 7. A varist is a component that changes resistance with the amount of voltage impressed across it. With little voltage across it, its resistance is higher. Then, at a certain breakdown or firing voltage, its resistance decreases dramatically. Number 8. Negative resistance is where the current through a component actually decreases as the applied voltage across it is increased. Some electron tubes and semiconductors diodes, most notably the 10-short tube and the Isaac or Tudor diode, respectively, exhibit negative resistance over a certain range of voltages. Thank you for watching. See you next time.